Now, children, we will discuss in detail about next type of semiconductor, the extrinsic semiconductor, that is called p-type semiconductor. As the word P indicates the positive charge, and positive charge means basically the holes. Now, this will just opposite to n-type semiconductor. Okay. Now, this is also one of the type of extrinsic semiconductor. Okay, obtained by adding what? Not pentavalent now. This time what? Trivalent impurity atom to a pure semiconductor. Now, trivalent means valency 3. Valency 3 means valence electron also 3. Okay, so when you add a trivalent impurity atom to a pure semiconductor like silicon or germanium semiconductor, then what happened? This semiconductor which is formed is called what? P-type semiconductor. And the example of trivalent impurity atoms are like, say, boron, okay, aluminum, indium, etc. And these are all the elements present in group 3 of the periodic table, having valency 3 and valence electron also what? 3. Okay. Now, as soon as when we add this impurity atom, trivalent impurity atom, to this pure semiconductor, that you can see that trivalent means how many valence electron? 3 valence electron. So 3 valence electron will share with the neighboring valence electron of this silicon or germanium atom. Like this is one of the valence electron of this trivalent impurity atom. Okay, is sharing with the one of the valence electron of this silicon or germanium atom. Similarly, this is one of the valence electron of this trivalent impurity atom sharing with one of the valence electron of neighboring silicon atom or germanium atom. Similarly, this is one of the valence electron of this impurity atom sharing with the valence electron of the silicon or germanium atom. So when they share these electrons, they form what bond? Covalent bond. So these are nothing but what bond? Covalent bond. Because you know covalent bond is always formed by the sharing of what? Electrons. Okay, but even the valence electron has been shared by this impurity atom. Okay, there remains an space, empty space. Now this empty space which is created will call as what? Holes. So whenever there is an empty space which is created, then this empty space is usually called as what? Hole. That's why there remains an empty space, and this empty space is simply called as what? Holes. And this hole is also called free holes. Free what? Holes. That means for every impurity atom, when you add trivalent impurity atom, if you add to the pure semiconductor, one empty space is always created, okay, or vacancy will be created, and this empty space is basically called as holes. So that's why, so when we add number of impurity atoms, so many empty space or free holes will create it. Okay, free holes will be created. So in case of this p-type semiconductor, number of free holes which will be created throughout the crystal, okay, depend upon how many impurity atoms that you are adding. Okay, how many impurity atoms are what? Adding. But you know what happened when this semiconductor is connected to an electric field? Means when you connect this to a battery or cell. So what happened under this case? Then electron which are bound to the neighboring this silicon or germanium atom get dropped into the what? Holes. Some electron will get dropped into the holes. Like suppose one of the electron of this silicon or germanium atom get dropped into this hole, or it may drop from here to like this and all. So what happened? And this neighboring electrons, okay, of silicon germanium atom, when it drop into the holes, then again there will be a vacancy which is created, and that vacancy is also called what? Hole. But this dropping of electrons into these free holes means actually due to what bond? By breaking which bond? Covalent bond. And when this covalent bond will break, so when you apply the electric field, and if you apply more electric field also. Okay, so when this semiconductor is connected to an external electric field, then this breaking of covalent bond may takes place. Okay, so that the neighboring electron, okay, may drop into these free holes. So that again there will be a hole which is created. So under this condition, this impurity atom, the trivalent impurity atom which has been added, okay, is also called an acceptor atom. So we call this now as what atom? Acceptor atom. Acceptor what? Atom. So why this impurity atom is called acceptor atom? Because they create holes. They create holes by accepting electrons from the neighboring atoms. Okay, this acceptor atom create holes by accepting okay, electron from the neighboring atoms. That's why this impure semiconductor, which is formed by adding trivalent impurity atom, is also called what? P-type semiconductor. Now the word P means positive. Now the positive charge carrier holes will be the excess or majority charge carrier outer, okay, and they conduct electricity. That's why this impure semiconductor is also called P-type semiconductor, because it has excess of what? Holes. So many holes will form, okay, as a what carrier? Charge carrier. And this is just opposite to the N-type semiconductor. Now we will discuss in detail about this band structure of P-type semiconductor, also called energy band diagram of this P-type what? Semiconductor. Now in this band diagram we have two bands, as you can see. There is valence band and there is a what band? Conduction band. But other than this valence band and conduction band, there will be an energy level. This is be occurred by the free holes which has been created, okay, due to the addition of this trivalent impurity atom. Now number of impurity atoms that you can, when you add to this type semiconductor, so number of free holes which will be created. Now these free holes already acquires an energy level, and this energy level acquired by the free hole by adding number of trivalent impurity atoms, okay, to the semiconductor will be just above the what? Valence band, just above the valence band, okay, and this energy level will be almost 0.01 electron volt in case of germanium and 0.05 electron volt in case of what? Silicon. So for germanium, this energy level acquired by this free holes will be just 0.01 electron volt, okay, above the what? Valence band, and 0.05 electron volt for silicon just above the what? Valence band, okay. And this level of energy acquired by these free holes is also called acceptor levels. And why we call this level is called acceptor level? Because at room temperature, at what temperature? Room temperature, the electron from the valence band can easily move to this level, energy level, and occupy the space created by the what? Free holes. Okay, that means the electron from the valence band can easily thermally excited and go into the which level? Acceptor level, okay, in this level of energy, and to fill the space which is created by the free holes. That is the reason that this energy level accept the electrons that goes to this energy level, okay, by accepting the electron moving from valence band to this level. So the energy level which is acquired by the free holes, these free holes present in this just above the valence band, okay, is also called acceptor level, okay, and this energy level will be just above the valence band, as I said already, okay, and this level accept the electrons which are excited thermally at room temperature, and they move from valence band to this level. So when this semiconductor is maintained at room temperature, okay, the electron in the valence band get thermally excited and can easily move from this valence band to this level, okay. So whatever free holes was created, this free holes space will create filled by this electron moving from this valence band to this level. And as soon as the electron move from this valence band to this level, holes will be created. And in this case what happened? More electrons, free electrons, okay, more electrons from the valence band move into this level, whereas very few of the electrons can go directly from valence band to which band? Conduction band. That's why if you look at the diagram, they are the electrons present in the conduction band, and this electron which present in the conduction band is also moved from the valence band only, okay, but minority of the electrons can move from valence band to the conduction band, and majority of the electrons can simply go from valence band to this acceptor level, where the holes, number of holes which was created in this level, okay. That's why majority of the holes that will be created in the valence band, and minority of electrons that will be present in the which band? Conduction band. So valence band have majority of the holes, and you know why holes are majority out there? Because most of the free electrons can simply move, okay, from valence band to this acceptor level, okay, whereas few of the electrons move from valence band to the which band? Conduction band. So in this energy balance diagram, if you see, holes which are the main charge carrier in valence band and the majority charge carrier, because holes are majority whereas electrons are minority. So where these electrons are these are the electrons. These are the electrons and this is actually called hole. So this semiconductor is also called p-type semiconductor because holes are the majority charge carrier while electrons are the minority charge carrier. So under this case also you can see that the concentration of hole in the valence band is more as compared to concentration of electron in the conduction band. So I write down simply NH. So I am writing NH is the concentration of hole is much large compared to the concentration of electron. Okay, but hole concentration is nearly equals to the concentration of the acceptor atom. The acceptor what? Atom. And this acceptor atom is given by Na. Or this is Na is also called what? Concentration of what atom? Acceptor atom. Concentration of what atom? Acceptor atom. Acceptor atoms. Now acceptor atom means the free holes which are created in this label, acceptor label. Okay, so most of the electrons move from this valence band to the acceptor label. That's why the concentration of acceptor atom is nearly equal to concentration of hole, where only very few electrons move from valence band to which band? Conduction band. Okay, so this is the case where we can see in p-type semiconductor. So under p-type semiconductor, when this p-type semiconductor which so form is connected to a cell or battery, that means when you supply some electric field, majority charge carrier which flows to conduct electricity is the hole and minority charge carrier which flows to conduct electricity are the what? Electrons. So this is the detailed explanation of p-type semiconductor. And children, after going through this n-type as well as p-type semiconductor, you simply understood that this type of semiconductor where the conductivity can be increased to a large extent by simply adding the impurity atoms without increasing the temperature. So one of the best way in which we can increase the conductivity in semiconductor by adding the impurity atom, okay, without increasing the temperature. And they are nothing but n-type and p-type semiconductor. And both this n-type and p-type semiconductor has a practical utility, okay, for making electronic devices. You know, there are so many semiconductor or electronic devices which has been formed. It's all due to this p-type and n-type semiconductor. So this extensive or p-type or n-type semiconductor has practical utility. And the utility of this p and n-type semiconductor part we do from the next chapter. Okay, that is the last chapter that we do as per reduced syllabus. Okay, for class 12 syllabus. Okay, so we have completed the chapter that is semiconductor electronics. So we'll be doing the new chapter that is called junction diode. Okay, thank you so much.